Good morning, everybody in the lecture hall. Good morning, everybody on Zoom. Good morning to the many people binge watching for the exam, maybe in panic for accumulating all the knowledge you need. So today, this is the last week with actual material. I'm going to complete this part right here. Next week will be a celebration of the end of the semester, of the summer. There will be a quiz for everybody. You will play against the TAs with some prizes. And so yes, if you come to the lecture hall as much as possible, as many of you as possible next week, that's always a good way to be together and celebrate. So before I start with this lecture, I'm going to ask you two questions related to query languages, and then we'll proceed to the rest of the material. So I'm going to open the question, and here you go. So the question is, these are 4 adjectives, and I'm asking which ones of these characterize a well-designed query language. Should it be functional and or imperative and or low level and or declarative? We have a lot of functional and declarative, and this is the majority. And indeed, functional and declarative, these are indeed the 2 words. What do they mean? Declarative means that that's the opposite of imperative, right? In an imperative language, you say basically do this, do that, do this, do that, and while this is true, do this, and so on. So it's giving orders to the computer. But in a declarative language, you don't tell the computer what to do. You just say, here's what I need. I would like the selection of the projection of this and that. So it's more like the style of SQL, right? So it's a declarative language. A functional language means that it's typically a language that is like a Lego game of expressions. You basically nest expressions inside expressions. And the reason it's called functional is that you can turn the expressions of the language into a structure called a tree. And in fact, mathematically, it's absolutely beautiful because you can model that with mathematical functions that call each other. So this is the reason for functional. But basically, it means that it's a Lego game, functional. So that was my first question. And my second question, which is actually a consequence of that, is why? Why should a query language be functional and declarative? Why not imperative, right? Why shouldn't you use Python, which is an imperative language? Why not low level, right? So why should it be functional and declarative? Is it because queries can be parallelized with functional and declarative language, or is it so that an optimizer can make the query faster than it would have been with the literal execution of the user's query? Is it in order to delegate the details of the execution of the query to a machine rather than doing it yourself? Or is it because queries are more concise and easier to read and understand? So why do you think a query language, a well-designed query language, should be functional and declarative? So you like the optimizations, you like the delegation of the details, the queries are more concise, you like that one too? So the queries can be parallelized. You don't like it that much, the queries that can be parallelized. Well, in fact, everything is a correct answer. All of these are reasons why it's a good idea to have a functional and declarative language. And so the language that we are looking at right now, JSONic, is functional and declarative, so it fulfills all of that. And so does SQL. SQL is also functional and declarative. The difference between the two is that SQL is made for structured tables when the data is flat and homogeneous. And JSONic is a language that is sort of an extension of this that also works if the data is messy, when the data is nested and heterogeneous. So these are all of the reasons. Everything is a valid reason. And parallelism is actually super important because when you have a cluster of 1,000 machines and you just write a few lines of JSONic, spreads it all to the 1,000 machines, magically even petabytes of data. All right. So now I'm going to continue where we left off and keep in mind functional declarative. I will try to keep that in the back of our minds during today's lecture. I have an assumption, is that you've done the tutorials, right? Who has done the tutorials of JSONic? Most of you, right? Very good. So I assume this, and this is why now I removed a few slides compared to previous years, assuming you already have that. And so I'll focus more about getting a bit more advanced and explaining how this all works. So first, when you have a functional language, it is absolutely important to say what this language manipulates with all of these functions. And again, I insist these are mathematical functions, not computer science functions, so mathematical functions. So what do we manipulate? When in JSONic, it's easy. We manipulate these sort of things, like there's JSON in JSONic. So you remember objects, arrays, strings, numbers, Boolean, nulls. So we'll manipulate all of that. But most importantly, in JSONic, we manipulate sequences of items. This is something I repeat 100 times today, sequence of items. It reminds me of a lecture I had when I was a student that was called, I think, something like Gründung und Führung eines Unternehmens. And every question the lecturer was asking, the answer was Kundennutzen, Kundennutzen. Here is the same. The answer is sequence of items. Everything, absolutely everything, the expressions we'll be manipulating are sequences of items. These sequences of items can be heterogeneous in the sense that the items can be different things. We'll see this can be objects, arrays, integers, just heterogeneous, and nested, denormalized, because these items might not just be atomic, they might actually be trees, right? So it's all denormalized. Now, sequences of items are flat. If I give you a sequence of one item, we'll say it's the same as the item. So if I say an integer, or if I say a sequence of one integer, it's the same thing. There's no difference, right? Sequence is just flat. So if you want to return an integer, you just return a sequence of one integer. Second, they do not nest the sequences, right? So if you try to put sequences together, it's always flattened. Sequence is always flat. Arrays nest, right? You can put an array and an array and an array. Sequences, no. Sequences are flat. You cannot nest sequences. And you have a special sequence that is the empty sequence, doesn't have anything, absolutely nothing, right? It's empty. And so the items, when we say sequence of items, can be atomic values, strings, numbers, Booleans, nulls, and even dates and many other types. They can be objects. They can be arrays. They can also be functions, actually, in the language, but we are not going to bother with the functions today. But they could be functions, right? You know, even in Python, you can manipulate functions, right? You can return functions and store functions in variables. This is useful for machine learning models. In fact, we do have this, but today I just look at atomic values, objects, and arrays, which you know because we've covered them many, many times across the semester. So any sequence of items is just a sequence with atomic objects and arrays, can be mixed together in any way you want, flat sequences. And every expression, building block of JSONic, takes and returns a sequence of items. Can take multiple sequences of items and output a sequence of items, right? So now it's a big Lego game. I'll show you expressions. There's 37 of them, and they all return sequences of items, and you can just combine them like a Lego game. Now, why do we have the sequences of items? This is the trick to manage nestedness and heterogeneity, because you can have sequences that are super unstructured and heterogeneous like you have on the right. And then you can have a bit more structure, like a sequence of one array or a sequence of arrays or a sequence of objects, sequence of Booleans, sequences of integers, going from the right to the left, one string or the empty sequence. It's a whole spectrum of things. And now, do you agree that the one in the middle, this sequence right here, do you see that it is a relational table? Who sees that? It is a relational table with two columns, foo and bar. Foo is an integer, a bar is a Boolean, right? So this is a relational table. So do you see how it's a superset of what SQL can do? It can also manipulate relational tables, but it can also manipulate individual values. It could also manipulate super messy sequences, right? So that is the secret. Now, you've seen in the tutorial that you can navigate the data. So very quickly as an animation, you might have here this object on the right. You can open a single document with JSON doc. JSON file is for opening a file with billions of JSON objects. JSON doc is a single one to start with. And now you see we can navigate. Dot countries is going to go inside that object and take the value associated with countries. There's only one. And if you continue by opening the array that is going to give us a sequence of 5 items, right? Because it's a sequence, it returns sequences of items. So that returns a sequence of 5 objects. Do you see that at that point, that's a relational table too? This sequence, it has 2 columns, name that is a string and code that is a string. So this is in fact a relational table right now. And then dot name, now it's a sequence of strings. That's no longer a relational table. That's a sequence of 5 strings, right? And you see how the dots go on all of the objects. You navigate somehow in parallel, right? And in fact, this will be implemented in parallel on the cluster, how you navigate through the objects. And you can also do dot code if you want. And then you have this predicate filter with the $$ that refers to the current item you're testing. And every item is tested for its code. So $$.code is going to be evaluated on every one of these objects and compared with CH, and only the one that matches this predicate survives. So this is going to return the first object. Who agrees? Right? And so this is the navigation language. The sources of a language like that are actually more on the XML side. So it's called XPath. So here it's JSON, but we also have that in XML. And in XML, we use slashes instead of the dot. And it's called XPath because the way it works is reminds you a bit of a file system when you have slashes that separates the directories. But again, the magic of the language is that when you navigate with a slash for XML or with a dot for JSON, you can be manipulating at the same time millions of objects, dot name, and then you create a sequence of, again, millions of objects, but every time you went inside the object. So that is navigation. And you see how compact it is, right, the query. This is an example on the GitHub, Git archive sample. So this is what you'll have at the exam, right? This data set, it's public, it's shared on the core, so it will be if it wasn't done yet. And so you see, JSON file now opens this file. It has one JSON object per line. It's called the JSON lines file. And then .payload is applied to every object, and then .commits to every one of the objects returned by payload. Then we pop open the array. Commits is going to be an array many times. .author, .email. And if at any point, if it's heterogeneous, payload or commits, payload is not an object, or commits is not an array, or author is not an object, it's no big deal. Then you don't return anything, right? So it's all flexible. It's not going to throw an error. .payload will return something whenever what you apply it on is an object, and it's just not returning anything if it's not an object. The square brackets on commits will open the array and return its contents if it's an array. If somewhere, because the data might be messy, it turns out that for some of the objects, the data at .payload.commit is not an array, no big deal. Then you just don't return anything for that object, right? You see the flexibility of that with heterogeneous data. You can use also number predicates, very convenient. You want to open a file and just look at one object, then just use the square brackets 1, that's position number 1. We start counting at 1 in JSONic, and that outputs the first object. You can, that's part of the tutorial, right? You can call keys on a collection. It instantly returns the keys. And I insist that this also works if the data is a huge mess, right? If the data is a huge mess and you have billions of objects with keys all over the place that are not even the same in all objects, this is going to efficiently find all of these keys. It's going to do it on a cluster. It's going to look at all the objects, even in parallel on the cluster, find out what the unique keys are, and return them. With just this, I would say one line of code, because I just formatted it on 3. It's one line of code. With one line of code, you find the unique keys on petabytes of data, billions of objects in the whatever is that location. Okay, then you can count and so on. So count is also very efficient. You can count billions or trillions of objects, absolutely no problem, just like a Spark count, right? So it's absolutely no problem to open data sets that have billions or trillions of objects. Counts will just efficiently count them if in parallel, if necessary, on the cluster. So for the exam, we give you just one sample of these, but in fact, if you really want to play with that, take it further and you want to, I don't know, create a cluster on Amazon with EMR, can be done with just a few clicks in a few minutes, then you can download one file for every hour of the past decade and more, even more than a decade. And you can just upload all of these to your data lake, S3, HDFS, it doesn't matter. And then you can write a query like count JSON file and a star to mean everything. It's a joker. And this, in that case, returned, there's so many digits that I have to think 2 billion, right? This is a query I actually executed. I took these files, I put them in a cluster, executed the query, and in just a few seconds, I got the answer, right? Just because it's all done in parallel on the cluster, right? So now you can construct, because it's a declarative language, strings in this way, or booleans and so on. What's nice in a JSONic is that you can just copy-paste any JSON, right? Strings, booleans, and so on. You just copy-paste it in the language, and it just returns itself, right? The same goes with numbers. You should just be aware that in JSONic, if there's no decimal period, it's going to create an integer. If there is a decimal period but no exponent of 10, it's returning a decimal. And if there's a scientific notation, it's returning a double, right? Integer, decimal, double, these are all XML schema, JSON types, right? So the types we've seen before, right? This is not new here. And all the other types that we've seen a couple of weeks ago, remember in the lecture on the schema validation and so on, they're all here. You just need to use constructors, right? So you just need to use the name of the type that you want to have, and then you pass a value with the literal. Yes?
One question from the Zoom. Are true and false also strings? So for the string, also true or false?
For which one? Oh, true, false?
Yeah, true.
Yes. So you can also have a string, but in that case, this here will create a Boolean. This returns one Boolean value, which is true, and this returns one Boolean value, which is false. If you put it in strings, that will return a string, right? But here, since there is no quotes, that is an actual Boolean. Just like in JSON, actually. In JSON, you also don't put quotes around Booleans, right?
Yeah, so maybe, yeah, so the second question also from Zoom, can it handle JSON-L, so new line JSON?
Yes, it can, absolutely. New line JSON, so probably you mean JSON lines, right? So JSON lines files, absolutely. And let me show you. When you have this, you see this JSON file here, right here. This here is a JSON lines file. That's exactly what you mean here. The files that have one object per line, billions of them, this is exactly what you put in there. You put the path to these files, even with a joker if there's multiple of them, and you call JSON file, it opens that kind of files. Absolutely.
Yeah. Yeah, thank you. Yeah.
So you could download thousands of JSON lines files with each 1 million values in them, one object per line, and then call JSON file on it, and the count will say 1 billion, right? So this is
Thank you. Thank you.
All right. And by the way, here it's even cooler. You see the .gz. When you download these, they're compressed. It's just a zipped version of the JSON. And that works. You can also put the zipped version. It's going to unzip it, right? It will just know that, that it has to unzip it and then look at the JSON. Saves a bit of the number of bits to read from the disk. Okay. All right. So you can copy paste any JSON you'd like, numbers. You can construct even exotic values with any of these XML schema types or JSON types, which is the same, just passing the literal value, and that's going to just construct it, okay? You can also copy paste objects in arrays. That is JSON, right? It's well-formed JSON. Well, it's also JSONic. You can also make it work. So I go quickly, right? Because that's all in the tutorial. So I just refresh, but I go much quicker than I did in the previous years. You have arithmetics, plus, minus, multiply, div. Be careful, not a slash, div. The slash is because it's used for XML, which I don't cover in this lecture. So div, IDiv for integer division, mod for modulo. Just a warning, I said everything is a sequence of items, so you might have more than one item, right? So if you try to combine sequences of more than one item with plus or minus and so on, you're going to get an error, right? If you try to have a sequence with 10 items plus a sequence with 3 items, that's an error. You need one item on each side, right? 0 would be fine too. If you put 0 items, that's an empty sequence, then it's going to return the empty sequence, right? So it's not going to complain if it's 0. But more than one, you will get an error. You really have to make sure whenever you use these arithmetic operations, only one item on both sides, returned on both sides. Then we have a huge function library, all standardized by the W3C, the same standardization body that makes HTML. So these are all standard functions, concatenation, string join, substring, string length, and so on. Just a huge function library. Just like in Excel, you would have also many documented functions, right? So this is all what you have available. You have comparison, equality, greater than, lower than, and so on. It all nicely works, right? And or not, the Boolean logic also works like in any other language. Just use the explicit and or not. But now the really cool thing is that I give you a few of the pieces of the Lego game. These are only a few of them: arithmetics, comparison, logic, copy pasting JSON values, constructing JSON values. Now I said it's a Lego game because you can put any of these expressions inside any of the other expressions, just like you build a huge Lego construction. Here's an example. That is a query where I put expressions inside expressions. And how do you evaluate this? Well, it's just like a calculation, right? Like you would do in primary school with plus and multiply. 2 plus 2, I can replace it with 4. Then I have this object you see in blue, B, associated with an array, and then I have dot B. So that's going to extract the array, right? So you agree? If I say an object with a key B dot B, that's going to extract its value, right? Then I have an array, and I have these empty square brackets that open it. So that's going to open the array and take its content. But in that case, there's only one object. Then I have an object A associated with for dot A. So again, that's going to extract the value inside, right? And then 1 plus 4 is 5. And 5 to 50 is an expression that returns a range of values, right? Just like in Python and many languages, right? Who is with me? Who followed this? That this just evaluates to this, right? Just like a calculator. And that's magic because you can just do these compositions in any way you want. Here it was a simple one with only one item at a time, but of course in general, you can have sequences of items. So you have this list of 37 expressions, just like you learned in high school that there is a precedence between plus and multiply, right? So if I say 1 plus 2 times 3, that's 7, right? It's not 9. 1 plus 2 times 3. It's 1 plus 6, right? Because you evaluate the multiplication before the addition, right? That's what you learned in primary school. And so here is the same. There is a precedence between the expressions. But I'm going to be honest with you, I can never remember what that order is because there's 37 of them. I can tell you I do not know that order. So then it's pretty simple. Just put parentheses. Put parentheses, you're safe. Then you have the control over the order in which it's executed. In the worst case, you have useless parentheses, but it doesn't hurt, makes it also easier to read, right? And so one of the cool things that you can do with this is that you can basically build structures that look like JSON, except that it's not JSON because you nest queries. So you see, if you look at this here, you have something that looks like an object, but here that's not JSON anymore. This would not be well-formed JSON. Instead, it's a query that evaluates to something, and then it will put it associated with that, which is happening here. The same here. At that point, it's still JSON, but now I have an array. Now it's no longer a well-formed JSON. That's a JSON-y query in here, right? And so this is a for loop that iterates from 1 to 10 and converts them to a long. Long is a kind of integer, right? On 64 bits. This is what I get, right? So who sees that this query evaluates to this, right? You see it? Right? And so it's magic because you just do it dynamically, right? That's a declarative language. It looks just like JSON, except you have parts that evaluate automatically, dynamically, like this. Okay? Then you have more expressions that would be perhaps familiar with other programming languages, like you have if then else. You have switch, case, default return, right? Who has seen that in other languages? Right, that exists, right? These are data flow expressions. And yeah, just 2 examples. There's also a type switch, there's also a try catch, so there's a few others. Just a warning, this is not an imperative if then else, like you would have them in imperative languages like Python. This here is really a declarative if then else. So it means if the predicate is true, then that will evaluate to whatever is in the then clause. If the predicate is false, it will evaluate to whatever the else clause evaluates to, right? In fact, in some languages, you might have seen it in C, C++, Java. Do you remember this ternary operator with a question mark and a colon? Like you have something, question mark, something, colon, something. Has anybody seen that? Nobody, right? Okay, then forget about it. It turns out that languages like Java or C, they have something like this, except they use a question mark and a colon. But forget, if we've never seen that, then don't worry about that, right? But that should be intuitive, right? If then else, switch, and so on. But now we come to the most important expression in JSONic, the most important one. It's the equivalent of the select from where. In SQL, you have select from where. And in JSONic, you have what's called the flower expression. What we will see is that the flower expression is a better and more generic select from where. It can do everything select from where can do and more than that. So it's called the flower expression. Why flower? Well, F for L for let, W for where, O for order by, and R for return. Right. And I also think it's a recognition of one of my mentors called Dana Florescu. I think that another reason why the expression was called in this way, who is the inventor of an early predecessor of this language, right? All right, so this is what it looks like. And I start with the let clause because this is the more intuitive one. Let doesn't exist in SQL, right? You could argue that with the with clause in SQL kind of does that, but it's actually not quite as flexible as this one. So a let clause, like in any functional language, lets you bind a variable to a value and then evaluate what's in the return expression. So here you say let x equals 2, return x times x. But do not make the mistake of thinking this is an imperative language, because the way you should read this is not put 2 into x and then calculate x times x. That would be the way you think of in Python. No, do not think of it this way. Think like a mathematician. You're basically telling a mathematician what is the value of x times x, knowing that x is equal to 2. That is how to read that query. Okay, it's a functional query. What's nice with the let clause is that you can cascade it, and it makes it very easy to make your code very readable for other people and to decompose your thinking into multiple bullet points, right? So instead of having a gigantic expression like the one I showed before, decompose it into smaller steps with let, and every time you just create something bigger. That's an example here where we return the count of the distinct logins, knowing that the distinct logins are the distinct values in login, knowing that logins are the values associated with the login key in the actors object, knowing that the actors object are obtained from navigating into actor from the events object, knowing that the events object come from some JSON lines file that I read for some path, knowing that the path is gitarchivebig.json, right? For whom is that clear? So it's a hint for the exam. If you don't want to have these huge queries you don't understand anymore, just let, and you just decompose your reasoning into smaller steps in this way. Another kind of clause is the for clause. The for clause is going to evaluate what's in the return clause for every value associated with the variable in the for expression. So in here, it means we are going to create a sequence that contains 10 objects, one object computed in the way you see here, number x square x plus x, for every value of x between 1 and 10. And you get what there is on the right. Right? Who is with me? Right? It's basically for return. In fact, the for clause corresponds to from in SQL. But you see here, we apply it not to some data. We just created 1 to 10, but in fact, it would apply to data too, right? But the idea is that the for clause corresponds to the SQL from, and the return here corresponds to the select in SQL, right? So this would be a select x as number, x times x as square from, and then some table you can create it with values in SQL, 1, 2, 3, and so on, all the way to 10. Okay? So this is an example of for clause. And here is an example of how you combine them, because in fact, you can combine them. You can create a query that looks like for, let, as many as you want, return, right? There is no limitation. That is a big difference with SQL. In SQL, it has to be select from where and so on, right? Just one from. But here, as many fors and lets as you want. Here, I just put 1 for and 1 let, but you can have any sequence of them in any way you want, right? So here, I'm going to basically look at every object in my file that I bind to events one by one. Then for every one of these objects, I'm going to count the number of commits, which is the size of the array located at payload commits, right? And then for every one of these, I'm going to create an output with the event ID, associated with ID, and the number of commits. Who sees that we've just output a relational table? This is also a relational table, right? That has the ID, a string, number of commits, an integer, right? Even though the data might not have been a relational table, right? The data that I read from could be a huge mess, could be some objects that don't have a payload, or the payload is an array instead of being an object, and so on. And it still works. It's still going to work, right? So that's an example with for let and return. Then there is the where clause. Surprise, surprise, it's just like the SQL clause. So what this is going to do is iterate on all the values of x between 1 and 10, but only keeping those for which x is greater than 7, right? X minus 2 greater than 5. So it's only keeping 8, 9, 10. And then for those that survive, the where clause, 8, 9, 10, I output the square. So this query outputs a sequence of 3 integer items, right? Who is with me? Right. So now we have 3 clauses. But what's really nice is that, again, unlike SQL, where it has to be select from where, and that's it, in JSONic, you can have a sequence of clauses that go like 4, let, where, for, where, let, for, where, let, return. That works. There is no, it's flexible. There is nothing that constrains what you can do. You can repeat it as much as you want. Just two rules. The first clause must be a for or a let. You can just start with a where, right? That wouldn't make any sense. So the first clause must be a for or a let, and the last clause must be a return. In the middle, you do whatever you want. You can put any clauses in any order and repeat it as many times as you want, okay? Then we have the order by clause, same as the SQL order by, right? So there's no surprise here. It's just iterating, and then it's reordering the output by population, descending. And so here it's by population, and that's the decreasing list of countries by population. Just like for let where, order by can be anywhere. So you can have for let where order by, where let order by, for let where order by, let order by, where return. That is a perfectly fine for expression, right? Then I have group by. And group by looks again like the SQL group by, looks like it, but it's more powerful than the SQL group by. Because it can do something that SQL cannot do. Look at what happens here. I'm reading my file that contains a list of countries, so one country per line, let's say. I'm grouping them by continents, right? Like this, x.continents. That you could do with SQL, right? Group by continent, and then you would aggregate the other columns that are non-grouping, right? So the continent goes here, and I have one object per continent, right? But look at what's going on in the countries. In SQL, if you have another attribute, in SQL, you would be forced to aggregate it, right? Remember, if you learn SQL, you group by continent, but then you would have to say the sum of the names, it doesn't make sense, the count of the names, and so on, right? You would have to aggregate them with an aggregation function, right? Count, max, mean, sum, average, these aggregation functions. But in JSONic, you do not need to aggregate, because what is happening is the power of sequences. Because what's happening is that the moment you group by continent, the names will be grouped as a sequence. So all the $X here that you have here that are in the same group, you get a sequence of them, .name gets all the names, and then you get them all in the output like here, nicely grouped by continents. So what we are doing here is something that you cannot do with SQL. Right? And you see, the output is not a relational table. There's nested arrays in there, right? So we are beyond what SQL can do, right? So you can try it out, play a little bit, but this is the big difference with SQL. You are not obligated to aggregate the keys that are non-grouping. In SQL, you are obligated to do it, not in JSONic. And if you do not aggregate them, they just come as a sequence. For whom is that clear? Right, everybody, right? So I recommend just play with it and you will say it works nicely. Now, group by just like the others. So now you can have a flower expression that goes like for, group by, where, order by, let, for, group by, where, order by, let, where, return. Right? You got the idea. It's fully generic. As opposed to SQL that says it must be select from where, group by, having, order by, limit, offset. Right? In SQL, you don't have a choice. JSONic, you can have them in any order you want. Okay? So how does it work? That's beautiful design. What I have to say is that the people who designed the semantics of the flower expressions in a way that they are actually quite intuitive are some of the same people that designed SQL. Right? So the chair of the working group who designed the X-query language, which JSONic takes its expressions from, was a SQL editor. Right? So these are exactly the same people who learned the lessons of SQL and the limit of SQL and who generalized it to something that handles messy data. So here's how it works. And what I'm about to show you is something more formal, that's happening behind the scenes. What's important to understand is that the end user doesn't need to understand that, right? Because of the intuition, it's actually quite intuitive. But if you want to see what's actually happening behind the scenes in terms of semantics, then I'm going to show it to you now. So I take this example of iterating, so going through the values from 1 to 10, eliminating those not above 7, returning the square. So the way that this was designed is that you have all these clauses within the flower expression, and every clause generates what's called the tuple stream. It's not a sequence of items because the clauses are not expressions, right? They're clauses. So the first clause, I'm going one by one. The first clause is going to generate a binding from X to all the values from 1 to 10, one by one. The way you can picture that in your mind is with this visual that has the name of the variable in there and each one of the values that it is going to be bound with. It's going to be bound with every one of these. Then I have the where clause, which is an expression that returns a Boolean, right? So this expression is evaluated for every value of X. So here, false, 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 false. They don't satisfy this. And 8, 9, 10 return true. And then once you have done that, it's a where clause. So you basically get rid of everything that is in the false zone, and you just take the true, and you have 8, 9, 10 that survive. So after the where clause, this is your new tuple stream, right? X is associated with 8, 9, or 10. Then the return clause is evaluating for each one of these, the square, and returns this. So that is the tuple stream semantics with for and where. Who is with me? Right? Here's another one, for let return, just to show you the logic. So for X in 1 to 5, easy. That's just X, all the values between 1 and 5, one by one. Let is going to add a new binding. So you have one binding per column, this visual. And Y is X minus 2. So it's going to be minus 1 when X was 1, 0 when X was 2, and so on. Do you see that it looks like a data frame? Right? It looks like a data frame. And in fact, Rumble implements it with data frames. It actually creates data frame when it does it. So these are created as data frames in the memory by the engine. And then X times Y, we execute for every row of that data frame, for every tuple, X times 1. So 1 times minus 1 gives you minus 1, 2 times 0 gives you 0, and so on. Right. So this is the trick. Group by, another example. So we start with 4, easy, right? X is bound from the values from 1 to 5. Group by, so we need to evaluate the expression in the group by. So we group by Y, and Y is equal to X mod 2. Okay, so we compute X mod 2 for every value of X. 1, 0, 1, 0, 1, right? Just a modulo 2. It's the remainder through the Euclidean division by 2. And then group by, what does it do? Well, it's going to put everything that has the zeros together and everything that has the ones together, like this. Do you see what's going on? 1, 3, and 5, they're associated with 1, so they go together. 2 and 4 are associated with 0, they go together. The power of sequences, because X can be a sequence. The language supports sequences of items. So now we have this tuple stream on the right where X, in the first binding, X is associated with the sequence of 3 items, 1, 3, 5, and Y is associated with 1. In the second binding, X is associated with the sequence of 2 items, 2, 4, and Y with the sequence of 1 item, 0. Right. And then return. So then foo Y bar count X, that gives us 1 and the count is 3, and 0 and the count is 2, right? So this is the power of tuple streams, the tuple stream semantics. This is how you generalize the select from where that you had in SQL that is very rigid, not flexible at all, that imposes an order. And now you have this generalized to absolutely any order of the clauses, with just the rule that the first must be for or let, and the last one must be returned. That's the only rule. Okay. That's an example where you do it on real life. So here I'm looking at the collection. It's a JSON lines file, right? I imagine 1 billion of objects in that file. I group by the number of commits. So the number of commits is just, I look at the size of the payload commits, right? But with a trick, because I told you it's messy data. So it might be that in some of the objects, even payload commit is missing, right? It might not be there. But that's not a problem because now I use a trick. If it's not there, I take 0, right? So look at what's going on here. I return the size. So if that actually exists, I take the first item in my sequence. So if that exists, that's going to be taken. In case that the array does not exist and commits doesn't have anything, that's an empty sequence, size returns an empty sequence. The empty sequence concatenated with 0 gives you the sequence with just 0. And the first item of that is then 0. So that is just a shortcut. It's a trick to say, if that doesn't exist, if there is no such array, because my data is messy, just fall back to 0, right? I could also have used an if then else, right? If exists size blah, 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 then size blah, 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 else 0, right? So it's just for the power user, the more compact form. Then we order by the number of commits, and then we return the commits and the count. And you see it's nicely ordered by the number of commits, 0, 1, 2, and I see the counts right here. All right. So that is an example of what you can do with JSONic. Which brings us to the break. And then I spend most of the time in the second hour giving you the internals of RumbleDB and how it's working inside, how it's mapped to a data center with thousands of machines. All right, so I'll see you at 16 past 9 for the second hour.